This approach retains a bunch of old networks, not just one, but a bunch of them. And these are called source networks in this model. And what we are doing here is this is actually more elegant, I think. We're learning the mapping between these old source nets and newly introduced hidden units. And since this seems applicable to RNNs, you see there is this flexibility that is very important to transfer learning algorithm. This is quite flexible. And this seems more general and less ad hoc, although I know that some objections have been raised against frozen networks. So of course you can also change the old networks too. Why not, right? You don't have to keep them frozen. So maybe you should think of it as well, this had to be really flexible, but you frozen networks aren't so flexible because they are frozen. Okay, so the Brusum algorithm uses enforced subpopulations method. It's a neuroevolution approach here. And the ESP algorithm evolves the network components separately in subpopulations. So this achieves some decoupling, easier to parallelize, it has some benefits. And it's been seen that this performs particularly well for reinforcement learning in partially observable Markov decision problem type of environments, and the transfer connections. That's a great term. It's something to remember, right? Transfer connections of each source net evolves separately. So this is the extension to ESP that ties it to the Brusum model, and the algorithm actually evolves transfer genomes. So that's also very reasonable. It sounds very very logical. Yeah, so we have frozen train networks, which means we're not modifying them anymore, and where there's a transfer network subpopulation, and there are new recruits. With the recruiting, I think it's a term used in neuroscience a lot. So the brain is recruiting new resources to adapt to a new environment, right? This is a very important feature of the brain, which we know is plasticity. So we're adding more plasticity to RNN training algorithms with this method, which is pretty cool. And I think I didn't try this algorithm myself, but I think it would be worth a shot, definitely. Well, and here we come to the conclusions. There aren't just a few, but there are many update algorithms that are applicable, readily applicable to induction. The generality of these update algorithms are usually limited, so that seems like a limitation here. And these algorithms usually see some synergy with the training method, the basic search method, whatever that is. And the experiments show that these algorithms are all experimental, not just theory, and that transfer learning works, it's effective. And some common strategies in these designs are, well, we usually need a way to represent programs, efficiently, of course, and we need a way to calculate the program probabilities. That's where a lot of novelty is introduced in these algorithms, if you would remember. And we usually copy some subprograms. Oh, I'm sorry, my battery is running out. I'm done. I'm going back over. Yeah, supposedly they invented the graphene battery, but he didn't bring it from China, so we don't have it here. Right? Graphene batteries. Yeah, they were just unveiled. Fantastic. Okay, now I'm failing. Okay. Sorry. It's just want to open. Yeah. Okay, so we need a way to calculate program probabilities, and we need a way to copy useful subprograms, usually. And we also need these clever methods to explore the model space efficiently and by introducing as much variation as possible. That's what I try to mean by flexibility, but flexibility, plasticity, and this exploring the model space, these are all the same thing, right? Basically. And there are also some universal heuristics in these algorithms usually. So, for instance, the larger programs mutate more kind of heuristics. These are universal because they're applicable to any program, right?
So about useful subprograms. I mean, that's something we struggle with a lot in Moses within OpenCog. Because
everyone struggles.
When you learn a bunch of programs,
yeah.
I mean, they're not naturally organized in a way that they use the same subprograms to do the same thing. And I mean, as a software engineer, finding the right way to abstract the functionality into a modular subprogram requires a lot of general intelligence. So that's something where there's a risk that the AGI you're after needs to be deployed in order to refactor your programs in a way that factor out the useful subprograms, or maybe there's some magic recursion that can be used there where the...
There's no magic.
You sure?
Yeah, I'm sure.
How about graphene?
Graphene is natural magic, right? It's physics.
Okay,
it's
natural.
It's natural magic.
I guess the point is that if you need some kind of AGI to identify useful subprograms among programs with heterogeneous syntax but kind of similar sub-functionalities, then how do you get that done? Do you somehow use the overall incremental induction to solve the find subprograms problem, or what?
Well, that's what I try to do. There are conceivably other ways. We don't know. So that's an open problem, and that's why I'm mentioning this. These are somewhat open problems, right? And I gave the example frozenness. So what would you do there? You just keep all the old nets you happen to train during your past lifetime. Is that what you would do? How do you determine which frozen network is more useful? How do you determine if you should call that network or if you should evolve that more?
I think that's only good enough in the limit of like infinite program ensembles. When you have a smaller program ensemble, you somehow have to be able to recognize when different programs have subprograms that look different somehow but do the same thing, which is what we try to do in Moses by normalizing the syntax.
Canonicalizing the program representation.
Which is also hard, no?
Yes, it is also expensive.
Yeah.
So I tried to drive a bound for that, general bound, and it turned out to be expensive.
Yeah.
And then I found this other thing about that the most general problem is actually incomputable, right? So because there is not a canonical representation.
Well, what really matters, as you say, is the average time it takes over the space of programs that you care about for solving your problems.
Exactly. So maybe that's why attention is so important, because when we look at a scene like this, we don't attend to all the details at once. And it's actually a lot of neuroscientists like Graziani. They seem to suggest that attention is at the very center of what we call awareness or consciousness, right? So a lot of neuroscientists are saying similar things. So maybe there's some kind of synchronous there. So maybe attention is a solution to that. At least in the sensory domains, it seems to be the case. And there are very good models that integrate attention into deep learning models. So, I mean, those attention models could be incorporated here, maybe. Useful, interesting.
It seems like the focus of attention is where the programs get normalized, right? I mean,
Ideally,
yeah.
the utility of a program lies solely in how many more times it is going to be called.
Or the programs that it leads to the creation of.
Of course,
right?
called
The
for
fitness of its children, the inclusive fitness.
by future solutions.
Yeah.
So that's why my model is the correct one, I think, because it does state induction, and state induction has very nice generalization here. So that I thought was the perfect solution. But anyhow, there might be other concerns here that we just don't see now. And but to see those concerns for sure clearly, we need to make more experiments, complex experiments, not just play experiments. So that's what I'm trying to get to. So well, yeah, there's some room for improvements, and this is not bad news. It means we know that we can improve them. So there's room for research and some interesting design parameters here. Generality versus efficiency trade-off. So the more general these algorithms become, more overhead they can cause. Like the canonicalization algorithm, right? So we try to make it very general, and then we run into some other overhead problems. So the trade-off there is actually interesting from an algorithm design standpoint. And how many free parameters do we have in the update algorithm? That's also interesting, because we don't want to have too many, of course. And does it have synergy with the search algorithm? Because if I suppose if all these stars and planets align, it works better, right? So it's this program representation and probability model and search algorithm and update algorithm, if they all work together, it's probably going to be more efficient. And some research challenges. Okay, well, learning very long training sequences, like more than 1,000 problems, that would be a challenge. And very interesting class of experiments, and this is what I'm trying to do in my research. And of course, demonstrating competence in a non-trivial field of expertise, the kind of field that is in intricate concept net like I showed you, and tests that are deliberately designed to measure memory performance. Just how good is the performance of this long-term memory system? So do we have the right test for it? It's an open problem. And and what would constitute human-level performance in that regard? And of course, as Van Gersel mentioned, there is the extremely important problem of integrating different modalities like vision, audio, tactile, haptics, touching, feeling, that sort of thing, and bringing these all together, of course, and maybe more, like sonar or whatever. And of course, architectural considerations to make this all work together well. We just mentioned attention. Attention is probably a very important part of this. We haven't really any experiments that show this in the context of universal induction, but we have a lot of neural network experiments that are exclusively about attention. So that's, I think, very important. And of course, we need some more substantial research towards zero free learning parameters, meaning there are no free parameters at all. It's completely general. It doesn't need any tweaking at all. There is no parameter mining involved. So that will be a nice thing. And here are the references. I'll upload this so you can have a look yourself later on. Thank thanks a lot for making enough. Yes, questions, please?
I have a question regarding choice of reference machines.
Yes,
So
yes,
in
please.
addition to the fourth light machine you mentioned,
Mhm.
in 2011, Vaness and Lake
Mhm.
used a VF reference machine. What are your thoughts on choice of reference machines?
Well, now I stumble because that's an open problem. That's one of the major challenges in, I think, universal induction research. So we certainly don't have the perfect reference machine. It could be something like neural networks. My preference, as I said, would be a very high-level functional language because yes, you have short programs there. But maybe it's a completely different kind of language that we just haven't designed. Maybe it's something like an object-oriented language.
Well, if you take a physics view, shouldn't the correct reference machine somehow be the one in which the laws of physics are extremely concise?
Sure. I mean, that's what my
Unless you take
ultimate intelligence stuff was about.
Schmidt-Huber's view that if our universe is just an arbitrary one among a bunch of universes, then it should be the one in which the universe generating function is concise. But then we'd have to hack out of the simulation department.
Well, or create a few baby universes to see how that works. But I think the general idea there is correct. So since we seem to live in a predominantly physical world, physical modeling seems important. So the language that allows us to model physics concisely is going to be useful. But there might be no silver bullet there. It still might depend on the domain. Say, like, if you have this nanoscale nanobot, maybe the right reference machine for that robot, and the right reference machine for the
Femtobot.
the femtobot, yeah, and the right reference machine for us crazy AI hackers. Maybe it's not the same thing because we need to climb up the tree and pick an apple or something, and while the femtobot is supposed to solve a completely different variety of problems.
Can you mention some practical implementations or applications that you've done incremental learning?
Yeah. It's. I mean, I worked on. I first started working on these toy problems, but I'm actually trying to come up with a set of. Right now, I'm trying to work on some scientific problems. I'm asking around people if they have interesting problems from sensory domains, like stuff where some real physical measurements are made. Because that's kind of interesting because sometimes there are non-trivial relations in such data sets. And I mean, my hypothesis there was you won't find that kind of a problem in the business domain. Usually not, because it's more like I think they are just different scales, just like what we talked about.
I was wondering, what was your intuition in terms of using, for larger programs, you said the mutations were done more, and
Well, they said it was empirical in the paper, so you should have a look at the paper and the part
because
of
it seems like that would lead to overfitting in the
Yeah,
wrong
it-
direction.
Interesting, yeah. So I think more experiments are needed to really understand or better here. But yeah, I agree. It might be flawed maybe. Then you see, if you make few experiments, then you get this other maybe it was something like that. Maybe it wasn't quite what they needed. I don't know, to be honest.
Did you consider using, rather than using context-sensitive languages, other weaker forms of representations, like context-free?
Yeah, well, yeah, I did that, right? So that's quite practical. It works.
So thanks for your talk. I wanted to get your input on the following. Oftentimes we think about incremental learning as you laid it out here as learning a sequence of different problems. But
Mhm.
for us and many other animals, of course, we actually practice tasks over our life.
Mhm.
Intermingled with practicing of other tasks, which
Mhm.
makes an incremental sort of add more neurons, that type of thing, not very likely.
Well, so what does that mean?
Well, the question is, the question is that how do you see the practice of tasks being dealt with in the paradigms, I guess, that you presented?
Okay, well, I'm not sure if I can give a good answer that, but I'll try. Is I suppose one of your concerns is whether this formalization, incremental learning, training sequence, is human-like or not, right? Is it actually what humans are doing? I think, well, actually, in a lot of the ways, this gruesome model does seem a lot like the brain. Why? Well, I mean, they use it in a reinforcement learning setting, right? But you don't have to. You can use exactly the same thing to solve mathematical induction problems or probabilistic induction problems. There's absolutely no limitation there, I think. So it doesn't really matter what sort of problem you are using, as long as it's, I think, one of those AI complete problems. But, and the second really cool thing about the gruesome model is, I think, well, it has some sort of modularity, right? Like, well, there are different areas of the brain, and these are, some of these networks are actually quite hard to change. Say we're acquiring language. We have Broca's areas and a few other associated areas, right? So these have to be fed with the right input at the right time, or they atrophy and cease to function properly, right? But then you train these, and you have these networks, and even in adulthood, these networks will make new connections. And it sounds just like the gruesome model. I think it's quite brilliant, actually. So yeah, so the same ideas should be applicable to human-like memory tasks. And this recent psychology research, do you remember? I heard recently that you get better at a task if you're a bit creative.